Once upon a time, a long time ago, Benjamin Franklin conducted an interesting physics experiment. He took a metal ball that had no electric charge, suspended it on a string, and lowered it into an electrified metal cup. He found that inside the cup, the ball wasn't attracted anywhere and remained in a state of equilibrium even though the cup was electrified. After that, he took the ball out of the cup, brought it close to the outer walls, and noticed that the ball started to be attracted to those walls. This only talked about one thing. Inside the cup, there is no electric field, and that's why the ball doesn't move anywhere. This interesting experiment was a precursor to the effect we know today. You've probably already heard that electric current is absent inside a conductor. You've probably heard that electric current is only present on the surface of a conductor. This is what's called the skin effect in the case of alternating current. The excess charge is distributed on a full conductor just like it is on a solid conductor. And basically, this experiment was later repeated by Faraday, and from these experiments, the famous Faraday cage was developed. Based on these experiments, an interesting phenomenon was later discovered for alternating electric current. For alternating electric current, it's known that its main, let's say, activity is concentrated on the surface of the conductor. This is what's called the skin effect. The skin effect is about the reduction of the amplitude of electromagnetic waves as they penetrate toward the center of the conductor. One might think that this pattern only applies to alternating current, and basically, the skin effect is indeed used in relation to alternating electric current. However, there is also an interesting phenomenon for direct electric current that is observed, which characterizes the uneven distribution of electric current across the cross-section of the conductor. Probably the most important question that comes to your mind is how in Frank's experiment it turned out that the charge concentrates specifically on the surface. Imagine we have a conductor that contains an electron gas. The electron gas is a kind of matter, some abstract matter that exists in metals, exists in conductors, and is basically a way to transmit electric current within the conductor. As long as we have a conductor, or let's say, a body that has an electron gas, or any other carriers, but it doesn't really matter, focus on the electron gas, because the meaning will be roughly the same for all conductors. As long as we have such a body, and as long as it is in a free state, the electric charges are distributed unevenly across it. They are scattered all over. Let's say the surface, the inner part, and so on. And now imagine that we have a body with an electron gas that enters an electric field. The process could be described using Gauss's method to solve all of this, but it wouldn't explain it physically. So it's important to have a clear physical explanation. What's happening here? Yeah, basically we remember Coulomb's law, which states that like charges repel each other, while opposite charges attract. And basically, when a body finds itself in an electric field, the electron gas tries to redistribute itself in such a way as to become organized. According to the principle we've outlined, this process leads to the concentration of charge on the surface of the body, with positive charge on one side and negative charge on the other, and then everything works like clockwork. Next is Franklin's experiment, where the attraction of the ball from the outside is quite explainable. Make one cup solid without a void inside, and make a regular metal cup with a void. Physically, it will be the same. The charge will spread evenly across the surface, whether in this case or that case, and all the charge will tend to concentrate on the surface of this cup. So we've got that very effect that Benjamin Franklin observed in his experiment. That's why the cup is charged on the outside. That's why the charge is distributed on the surface on the outside. The next point, we drop the ball inside the cup. So what do we have? The ball has no charge, so the electrode gas inside is organizing itself to achieve equilibrium. The electric field that formed the charge on the cup is also balancing the charge on the ball. It tries to distribute itself inside the ball in such a way that equilibrium is achieved, and basically the electric field that initially formed the charge on the cup is also trying to balance the charge on the ball that's inside. Now let's move on to the skin effect. And let's remember that this term applies to those conductors where we have alternating electric current. And basically, all the electric current, so to speak, is concentrated on the surface of the conductor. Inside the conductor, we can say that there is no electric current. Why does this happen? Let's recall the definition of electric current. That's also quite naive, but understandable. Electric current is the ordered, directed movement of charged particles. Charged particles move under the influence of an electric field. Where is it easier for the electric field to push this electron gas that we have in the conductor? Of course, it's easier to do this on the surface of the conductor. It's energetically more advantageous to push the particles that are closer to the surface. But besides that, there's another interesting effect, another interesting phenomenon. Keep in mind when we talk about the skin effect. The thing is this. We remember that we have an electric field, and there's also a magnetic field there. Again, we're really oversimplifying things here because it definitely needs a more detailed explanation. But for understanding the skin effect, that's enough for us. And we remember that alternating current generates a magnetic field. Inside the conductor, there are these swirling currents that will accelerate the current flowing through the conductor at the surface, while inside the conductor they actually hinder the current that flows within it. It turned out to be a bit of a tautology, but I hope everything is clear. So, it turns out that on the surface, this parasitic phenomenon, you could say, accelerates the electric current that is already present in the conductor, while in the center of the conductor, this same phenomenon hinders the flow of the electron gas. And that's why, of course, the particles try to move along the surface of the conductor. So, in the end, the skin effect is caused by two factors. The first option is the electric field. It's just simpler. Push the electrons, push the electron gas. By the way, all of this is of course an abstraction, but let's not get into that right now. It's a very big and long story. Let's stick to the classical concepts of classical physics. And so, the electron gas finds it easier to move where the electric field can push it more easily. The next point is the emergence of fields which are interconnected. In one case, we have a resisting force in the center of the conductor that prevents the electric current from flowing properly there, while on the other hand, at the surface of the conductor, there's a force that accelerates the movement of electrons along the surface of that conductor, and it results in quite a favorable position. The next point that is often remembered is the skin effect with direct electric current, and you can often read that the skin effect does not work with direct electric current. But overall that's correct because the mechanism we just discussed a little earlier really won't function, it won't work. But in our case there's another interesting effect. If you remember how Joule's law works, you'll understand that any conductor heats up when an electric current passes through it. In the case of direct current, the conductor heats up as well. And if we look at the cross-section of the conductor through which the electric current is flowing, we can find that the center of the conductor will be hotter than the surface. In the case of direct current, the conductor definitely heats up as well. And if we look at the cross-section of the conductor through which the electric current is flowing, we can find that the center of the conductor will be hotter than the surface. This is inevitable because heat is being dissipated from the surface of the conductor. When heat is dissipated from the surface, it makes sense to assume that the surface is cooler. And then there's an interesting effect. We remember that resistance is caused by, let's call it, the internal friction of the electron gas against the structural elements of our metal wire. And so, if the conductor gets very hot, its resistance increases. This is a well-known effect that is quite often described. So if you cool the conductor, the conductivity effect will be much more intense. Moreover, those who are interested in physics probably already know that there's something called superconductivity, and superconductivity works at very low temperatures. And now many scientists are working hard to achieve superconductivity at room temperature. As far as I know, there are some results, but that's not what we're talking about right now. So, it turns out that the conductivity of the surface of the conductor when direct current passes through it is higher than the conductivity in the center of the conductor. Well, where the conductivity is higher in the conductor, it's easier to pass electric current through it. So in the case of direct current, the skin effect is absent. It really doesn't work. But this interesting observation we just talked about does work. So indirectly, we can also say that the electric current in the center of the conductor is at least less, and we constantly use this phrasing. There's electric current, there's no electric current. On one hand, it's illiterate and physically incorrect to say it that way, but on the other hand, it's the simplest and most understandable description. We remember that electric current is the ordered movement of particles, and if there's movement of particles, then there's electric current, and if there's no movement, then there's no electric current.